Welcome, good morning, good afternoon, wherever you are in the world. On behalf of PsIP, it's my pleasure to welcome you to our second 2024 webinar on phytosanitary irradiation versus conventional post-harvest treatments, the food quality aspects. PsIP strives to be the go-to source globally for all information related to phytosanitary irradiation, and we feel happy to be in mission today to present to you Dr. Anuradha Prakash. Dr. Prakash is professor of food science at Chapman University in Orange, California. She teaches food processing and the preservation of food product development. She serves as a faculty advisor for the Chapman Coffee Club, which explores the science and art of making a great cup of coffee. She is a 2021 fellow of the Food Systems Leadership Institute and has served as a science advisor to the FDA Pacific Southwest Laboratory, now known as the Food and Feed Lab Southwest. She also serves on the board of directors of the Community Action Partnership of Orange County, an agency devoted to alleviating poverty. Her research focuses on evaluating the effect of irradiation on the quality of fruit treated by irradiation for insect disinfestation, with the ultimate goal of eliminating global trade barriers by reducing the threat posed by invasive pests. Dr. Prakash hosted the Phytosanitary Irradiation Forum between 2010 and 2018, which helped facilitate the use of phytosanitary irradiation worldwide. On a personal note, I can tell you that I've assisted many of these events and always have taken great knowledge and great expertise away from them, and it's been a pleasure to watch Dr. Prakash build such a prosperous and successful community. With that, thank you very much, Anu, and I hand you over the mic.
Thank you, Arved, for that very kind introduction, and thank you to PsIP for organizing these excellent seminars and for inviting me to be part of the quality seminars. I'm following up from John Golding, who did a wonderful presentation a few weeks ago on the impact of radiation on quality of fresh fruit. So mine takes it into a slightly different but related area, which is comparing the effect of radiation on quality with conventional treatments that are used in post-harvest. My agenda today is to talk a little bit, give you a background on conventional post-harvest treatments, specifically the ones that are used for phytosanitary treatments, and using a series of case studies based on work that we've done at Chapman, I'll describe to you the differences in quality as a result of various treatments, and then end up with some conclusions based on not just our findings, but what other research reports and suggestions for next steps. So as we all know, fruits and vegetables are highly perishable, making them very vulnerable to post-harvest losses. Microorganisms, insects, high metabolic rates, moisture loss, all of these can lead to loss of freshness, loss of nutrient quality, and just overall quality. Given the large domestic and international trade of fresh produce, they're subject to various treatments in order to extend shelf life and to facilitate trade and minimize quality effects. So these include sanitizers and cleaners that are used to remove debris and also reduce microorganisms, coatings of various kinds that are used to reduce moisture loss and also to reduce respiration rate and therefore extend shelf life. Fungicides are often added into the coatings to reduce mold decay. We have shelf life extenders such as modified atmosphere packaging and controlled atmosphere, especially for long distance shipment. On On the other hand, we have ethylene that is used to induce ripening for fruits such as mangoes and bananas, whereas ethylene blockers are used to reduce the effect of ethylene. 1-MCP is a common example. Scol inhibitors are used to reduce browning that might take place on fruits such as pears and apples. Sprout inhibitors are chemicals that are used on products such as potatoes. And anti-browning agents are used for various fruit to, again, extend shelf life, minimize browning, mostly in the flesh of the fruit. That leads me to phytosanitary treatments. These are pre-shipment or post-shipment quarantine processes that are used to inactivate pests that could harm agriculture or the environment if they were to get established in a new area. Various physical and chemical tests are used to exert this phytosanitary effect to either inactivate, kill, or remove these unwanted organisms. You could use a single phytosanitary treatment or sometimes used in combination with other processes to effect a positive effect. So I'll touch on a few of these, not all of them, maybe some of the more common ones. Hot water treatment are used often for certain tropical fruits, such as mangoes and papaya. They're easily installed in packing houses and have a much lower cost, and in particular compared to phytosanitary irradiation, right, or to other treatments even. They require higher temperatures for over 30 minutes. Sometimes it can go even much longer than that. And this hot water treatment can cause damage to the quality, both internal and external quality of the fruit, particularly skin scalding, darkened lenticels, and internal cavities. So to minimize these effects, fruit are often treated when they're fairly unripe so they can tolerate the heat treatment. Cold treatment is one of the most easy treatments. It's storing the fruit at anywhere from -1 to about 3 degrees centigrade for an extended period of time, which should go into several weeks. And so it's an easy way to exert the treatment during transit or even during warehouse storage. It's used for cold tolerant fruits such as grapes and apples. The disadvantage is that it requires a long treatment time, and some insect pests are not destroyed adequately. Also, there is the possibility of chilling injury if the fruit is not conditioned properly or exerted to a lower temperature than it can tolerate. Methyl bromide is probably the most commonly used fumigation technique. It's a broad spectrum fumigant. It has high penetration into the commodity and it vaporizes easily following treatment. However, methyl bromide fumigation releases bromine into the stratosphere, which ends up depleting the ozone layer. So its use is restricted. It's considered a class 1 ozone depleting substance. So based on the Montreal Protocol, it's being phased out. However, there is a critical use exemption that allows the production and consumption of methyl bromide for quarantine and pre-shipment purposes. So that leads us to phytosanitary irradiation, which is a non-thermal and non-chemical treatment, which is its greatest value. It's environmental friendly because it doesn't leave any residues and highly efficacious on insect pests. The great benefit is the use of generic treatments that facilitate global shipment. In many cases, it's the only treatment, such as for mangoes from certain countries into the US. And oftentimes, it's the best treatment option compared to other phytosanitary treatments that are available. This table compares some of the treatments that I've spoken about. This table is adapted from a recent publication that was authored by John Golding, led by John Golding. He included Dr. Aparadi from Thailand, Dr. Jesus Paz from Mexico, and myself. This was published just earlier this year. I highly recommend you take a look at it because it provides a lot of information for phytosanitary irradiation and its effect on quality. You can see the differences due to different factors, but I'd like to ask for your attention to the lowest line. Regardless of the treatment, there are impacts on quality. And the reasons for the impacts on quality is because most treatments that we use for phytosanitary purposes, but in general on fruits and vegetables, for long distance shipment and for long storage will exert some kind of stress to the fruit, and the fruit will respond in different ways. And so there's always that challenge of finding the right, the most appropriate technology that we can use to minimize effects on quality. So using a series of fruit as an example, studies that we've done at Chapman, I'd like to show you some of the results that we have. We've compared radiation with other phytosanitary treatments. I'll start off with a study on strawberries. Strawberries are highly perishable. They usually have a shelf life of, a few days, maybe a week. And when we export them from the US overseas, so California is a large producer of strawberries. When they are sent overseas, they're usually air freighted in order to get to make maximum use of the short shelf life. So the maintenance of the cold chain is very important for strawberry shelf life. In this case, we were comparing the effects of methyl bromide fumigation and phytosanitary treatment, and we were simulating air shipment to Asia. So these were the conditions in which the fruit were treated. We obtained 2 fruit varieties from Southern California itself. We stored them after treatment. We stored them overnight at 1 degree centigrade and then insulated them in a way to simulate air freight transport. After they were shipped for approximately 24 hours. We removed them from the insulation and exposed them to ambient conditions for 4 days, simulating their availability in a non-refrigerated market overseas. So on the left are pictures of how strawberries are freighted in air commercially. And on the right is how we did it on a smaller level at the university. But I believe that we came very close to what it might actually look like, except that it didn't get on a flight. So in this slide, I'm showing you the 2 strawberries. On the left are the Marquis, on the right are the Amado strawberries. And it's the effect of treatment on damage. We did 2 trials for each of these strawberries. This is showing you the effect of damage in percentage. So what would stand out is we air freighted them, and you can see that compared to radiation, the methyl bromide fumigated strawberries always had a much higher level of mold and decay. And this was generally true for all cases. The other thing that I'd like to highlight is there's a difference in how different varieties of the strawberries behaved. Marquis strawberries were different from Amado. Amado seemed to be much more sensitive to decay than the Marquis strawberries. But regardless, you can see that the air freight. And what I've not shown you over here is the effect of the controlled refrigerated storage, which I'll share with you over here. But really the challenge we see with fumigation is the fumigation requires the fruit to be held at a warm temperature for several hours. And that break in the cold chain, this is the temperature of the fumigated strawberries. So you see the break in the cold chain. And even though it's cooled down, during air freighting, the temperatures get up to, they increase to 30 degrees centigrade, maybe over more, even more. And it's not just during the air shipment, but it's at the airport, both before and after shipment. So you can see this break in cold chain is damaging to the strawberries. So strawberries, all of them developed mold within a few days. On the left is the control, in the middle is the fumigated, on the right are the radiated strawberries. So just the break in cold chain, the higher temperatures are difficult on the strawberries. But clearly the radiated berries had less mold than the fumigated berries. They were not particularly better than the control berries, which were not subjected to any treatment. In comparison to the fumigated berries, the shelf life extension was maybe 1 to 2 days at the most. Here's another study, this one on blueberries. In addition to methyl bromide, we also use modified atmosphere packaging, which is very commonly used in the food industry, in the fruit industry, to extend shelf life. So modified atmosphere works by reducing oxygen in the headspace of the fruit and increasing CO2. This reduces respiration rate, and it also reduces the growth of aerobic microorganisms, thus in both cases extending shelf life. So this was an experimental design. We received the blueberries from California. They were either treated with gamma radiation, 400 grays, or fumigated with methyl bromide locally at a commercial fumigation facility. And then they were packaged with modified atmosphere or not. So we ended up with 6 treatments. We had the control that did not receive any treatment and was not modified atmosphere packaged. We had the radiated only. We had fruit that was only modified atmosphere packaged, fumigated, and then the combination of radiation with modified atmosphere and methyl bromide with modified atmosphere. So we had 6 treatments. So this is a lot of data on this slide, but I wanted to show you the effect on firmness. We stored these blueberries for up to 53 days at refrigerated temperature, and blueberries can actually last for a long time, especially if they're packaged under modified atmosphere. And what you can see, I showed you this firmness because radiation is known to reduce firmness of a number of fruit, particularly berries. When we compare it against the control is the first bar, the second bar is the radiated only, you see a decrease in firmness. Methyl bromide initially did not have an effect on firmness. The modified atmosphere also helped to maintain firmness of the fruit. But the radiated with the modified atmosphere, also showed a reduced firmness in this case. But as you see, as the shelf life is extended, the radiated fruit does not lose any more firmness, whereas the fumigated fruit gets softer over time. And this shows even at the end of shelf life, actually the radiated fruit maintains its firmness quite nicely. So does the combination with modified atmosphere. But the fumigated fruit, in both cases, you see a great loss in firmness. And when you see, when we evaluate damage to the fruit, and so the higher bars show more damage, you can see that initially we do see damage In this case, it was mostly leaking fruit or shriveled fruit in some cases due to radiation, and definitely due to fumigation. As the shelf life increases, we see that increase over the control. But I'd like to highlight the ones that were packaged under modified atmosphere. So the modified atmosphere was the same as the control with no modified atmosphere, but the radiated one in combination with the modified atmosphere actually showed lower damage. And at the end of shelf life, that combination of radiation and modified atmosphere was much better than the control, was better than all the other treatments. This is what they looked like during different stages of shelf life. You can start to see some mold showing up on day 38 in the radiated, definitely in the modified atmosphere, even in the MAP packaged ones. But you can see clearly the much greater mold appearance in the fumigated blueberries, which are MB, and also the methyl bromide plus the MAP packaging. This was a really good study. Really proud of this study. This is a study in which we transported treated cherries to Vietnam. These cherries, we had the control cherries, we had the fumigated cherries, and radiated cherries. We obtained these cherries from Washington, which is the largest producer of fresh cherries in the United States. And we mimicked as closely as we could commercial freight conditions, right? So these fruit were harvested in Washington. They were trucked to Southern California, where we treated them with fumigation and radiation. And then we put them on a flight to Ho Chi Minh City. And in Ho Chi Minh City, my colleague there, Dr. Tuen at Nong Lam University, received them at the airport. And then he opened them up for ambient temperature display, as might take place in a wet market versus a supermarket. But then he also refrigerated them for 2 weeks and then presented them for retail display. So again, a busy slide, but this one shows you decay of the fruit that was in Vietnam, which is the top left, that was put out for retail display as soon as it was received. And you can see that the sweet cherries, they started to develop mold, and the fumigated was developed mold faster and much higher as compared to the control and the radiated, which were actually quite similar. We kept the same cherries, not the same cherries, but we kept a shipment of cherries within California. So these were not subject to air freight, right? And so they maintained quality for almost 9 days. And then you can see that all 3 treatments had high levels of mold. The lower graphs show cherries that had been stored for 2 weeks under refrigeration, let's say in a warehouse, and then sent out for retail. And you can see that within a few days, they develop mold, with the fumigated ones showing the highest level of molds. And the same thing, we saw that in California. It took a couple of days more, but they did develop mold eventually. So this clearly shows that fumigation is a tough treatment for some of these fresh fruit. There doesn't appear to be a direct effect of the fumigation. I mean, the methyl bromide itself, it really is the break in the cold chain that impacts the quality of the fruit. A more recent study is one on Granny Smith apples, which is a very popular apple that's grown in California and is exported to Mexico. Is a popular destination for these Granny Smith apples in particular. During post-harvest storage, and apples are often stored for many months after being harvested under cold temperatures to extend shelf life. But Granny Smith apples are sensitive to a number of post-harvest defects. One of the major ones is superficial scald. And superficial scald is this appearance of brown corky areas on the surface of the fruit, and it's actually occurs on a number of apples, but it's most visible in these Granny Smith apples because of their bright green color. The brown spots show up very quickly, and it shows up after the fruit has been in cold storage for several months, and then it's brought out to ripen at room temperature. And after about 7-10 days of ripening at room temperature is when these brown lesions will start to show. So the cause of the superficial scald is the cold stress, the chilling injury that takes place, but also during ripening, ethylene is produced by the fruit, and that seems to be a causative factor for superficial scald formation. So common treatment in the industry is DPA sprays, diphenylamine sprays. And diphenylamine is it's a lipid-soluble antioxidant, and it penetrates into the peel. So the superficial scald is just a peel phenomena. It does not go into the flesh, and it helps to inhibit scald formation. It's an antioxidant, and it helps to stabilize the cell membrane. The problem with DPA is it's considered a carcinogen, and for example, the EU does not allow use of DPA. The other common chemical that's used to inhibit superficial scald is 1-MCP, and it controls ethylene perception. So what it downregulates the genes that are responsible for the initial compound that causes superficial scald. So it takes place of ethylene on these ethylene receptors in the cells, and it downregulates the production of ethylene. So if ethylene is not generated, you will see an extension of shelf life. This is an example of pears, and you can see that they don't develop the superficial scald once they're treated with MCP. MCP efficacy decreases during storage time. So after a few months, the exposure to MCP starts to decrease, and these MCPs removed, with continuous ethylene generation, it replaces the MCP. So in our study, we obtained Granny Smith apples from within California. They were subject to gamma radiation treatment at 2 dose levels. They were also subject to fumigation. We treated them with DPA and 1-MCP. And really the idea of this study was to see, even though DPA and 1-MCP are not phytosanitary treatments, what we wanted to see is if this one radiation treatment could actually take the place, it could replace multiple chemical treatments. So methyl bromide as a phytosanitary treatment and DPA or 1-MCP as chemical treatments on the fruit. And this is based on a study that had been done, studies that have shown that radiation can decrease superficial scald in apples. So once they were treated, we stored them in cold storage for a pretty long time, 150 days. And then we would bring them out to room temperature and measure respiration rate, ethylene production, superficial scald incidence, and other quality factors. And then we would measure some of these compounds in the peel because these are the compounds that are responsible ultimately for superficial scald. So I'm showing you data over here for apples that had been stored for 90 days and then brought out at room temperature and stored for 7 days, and they started to develop superficial scald. I should say that we did the study for 2 years, and in the first year, the apples had very low levels of superficial scald. But in the second year, in the second set of apples, we actually saw high levels of superficial scald, which to us told us that anytime you do studies with fresh fruit, you have to do multi-year studies because the fruit behaves so differently from year to year. You can see the superficial scald in the control apples. The DPA was actually quite effective in reducing superficial scald. Methyl bromide was also seemed to suppress superficial scald, but what it did do was cause a yellowing of the fruit. And with Granny Smith apples, we want a bright green color. Consumers don't like to see yellowing on Granny Smith apples. One MCP was effective, but by the time we got to day 90, that effectiveness was getting reduced, so we saw some scald formation. You can see over here the gamma fruit treated at 240, and especially at 860, we saw high levels of superficial scald in this fruit. What was interesting also was when we cut open the fruit, we could see internal browning in only the radiated fruit, which tells us that there is a damage. In last time's presentation, PsIP presentation by John Golding, he explained how radiation is a stress on the fruit and it generates reactive oxygen species and free radicals. And this is a classic example of those reactions that damage the internal cells of the Granny Smith apples, allowing an enzyme called polyphenol oxidase to react with phenolic substrates and produce this brown color. So as I mentioned, we had done similar work previously with Granny Smith apples, and in that case, we had used X-ray treatment. And you can see that the controlled fruit develops scald, the fumigated fruit especially develops scald. But in that case, the radiated fruit that we treated at 250 and 1000 gray did not develop scald. We don't know if it was the fruit, if it was the treatment, but we had very different results when we tried gamma radiation in the most recent study. Here's a study that we did with pomelos, and we worked with two varieties of pomelos. This is the Chandler pomelo, treated at 2 dose levels, and we stored them for 3 weeks under ideal conditions of storage. And then we brought them out for 1 week at room temperature, so a total of 4 weeks. So with the pomelos, we saw that peel damage started to show up, and it became even more clear after that 1 week at room temperature. What was also very interesting is that we saw that when we handled the pomelos, so when we were moving pomelos from the cold storage into the lab for room temperature storage or for handling it to do these quality measurements, the radiated pomelos started to show a lot more peel damage than the controlled, kind of indicating to us that, you know, the radiation stress, even if it does not show up after storage, it could show up if it is subject to mechanical or some kind of physical handling. And some of these radiated pomelos also develop mold growth, and that's because of the compromise to the peel. So kind of to summarize all of this information that I have presented to you, we've seen, and you know, this is not just our work, it's other people's work as well, has shown that compared to methyl bromide fumigation, hot water dips, radiation is better in maintaining quality. Now, of course, if hot water dips are used quite a bit, and if the conditions are maintained properly, the people who conduct hot water dips, they know what they need to do. They know the maturity of the fruit that's necessary in order to maintain the best quality. But keeping all things equal, radiation can provide better quality as compared to those heat treatments. So the challenges with the heat treatments in those two cases. And those benefits of that radiation exerts are manifested throughout the supply chain, during shipment, during warehousing, and even during distribution. In some fruit, particularly in climacteric fruit, ripening is delayed, so it provides additional shelf life. In some cases, it might be as little as a day, like with the strawberries that are kept at room temperature. But in other cases, like blueberries, it could be a few weeks if they're stored under refrigeration. Having said that, radiation does not always maintain better quality. It's highly dependent on the fruit. It is a stressed, more, in some cases, it's more of a stress to some fruit than to other fruit. And subsequent handling can enhance the damage that we can see. In our study with 1-MCP and DPA, found that radiation would not replace those treatments as a way to reduce superficial scald. But as I mentioned to you, we got different results in 2 different years using different radiation modalities. So that suggests to us that additional work is needed over there. Also, what we've observed that right after radiation, if the fruit was being sent to the market right away, you might not see the negative effects of radiation. They might only show up after storage, after long-term storage. So the effects that we see on apples, we don't see that right away. We've seen that usually after a couple months of storage. And there might be benefits of combining radiation with modified atmosphere that might provide, in some cases, additive shelf life or synergistic benefits as well. So with the increase in the use of phytosanitary radiation for international trade, there really is a need to establish quality standards. But there's a lot of challenges in establishing quality standard. And, that's been our goal for the last few years, is to establish quality standards. But we have not been able to do it because of all of these different factors that impact quality of the fruit. So it's not just the treatment itself. Fresh fruit and vegetables are grown under different regions, different rootstocks, under different weather conditions. There's year-to-year variations. They're harvested at different maturity stages. All of these factors are so important in the quality of the fruit. And so it's very difficult to predict how that fruit is going to behave. I think it's going to take some modeling. We need data scientists to be involved over here to look at how all of these different factors might contribute and help to predict the quality of the fruit. This would have to be verified with controlled multi-year trials. And when I say controlled trials, I'm also talking about getting the fruit from the same farm, from the same trees every year. Because even if you switch farms within the same region, you could have different conditions, different quality effects of the fruit. These studies need to be taken out of the lab and made sure that quality and the impacts on quality can be verified under commercial conditions of shipment. And for fruit that are sensitive, evaluate dose levels or combination treatments that might mitigate fruit quality. So with that, I'd like to acknowledge there's so many people over the years, so many students and postdocs and collaborators that have been involved in these studies. This is not the work of just a few people. It's taken a team of people across nations to be able to do this work. So thanks to all of them. And also thanks to USDA for an agriculture service for the task grants that have made most of this work possible. And with that, I'd like to open it up to any questions that you might have.
If you have questions, if you don't mind, there's a question and answer box at the top of your screen. If you type your question in, and then we will read those out in the order we receive them. Okay.
Either my presentation was very clear or it was too complex.
I think it was crystal clear. With that, I would like to thank Dr. Prakash for yet another excellent presentation. Very enlightening. You will see that the phytosanitary irradiation is a growing community, and you will have many opportunities, I believe, to cross paths with Dr. Prakash again. So with that, I thank you. Thank you for attending, and thank you for helping us grow our community.
Thank you.